Hello, in this video we're going to look at some Hooke's law. So let's go through what looks like quite a lengthy question here, see how we get on. Bungee jumper, mass 70 kilograms, attached to one end of a light elastic cord, natural length 26 meters, modulus of elasticity 1456 newtons. Right, okay. Other end of the cord is attached to a fixed horizontal platform, a height 69 meters above the ground. Right, let's start drawing some of this out. So we've got fixed platform, cord, we got a natural length of, what did it say, 26 meters for the cord. We've got some woman stuck to the end of this. She's got a mass of 70 kilograms, so we've got a 70 g weight going down. We've got a tension in the cord going upwards. I'm guessing they're going to tell us that we've got, there we go, no air resistance, particle. Yeah, she falls vertically. Hooke's law assumed while the cord is taut. When Carol has fallen X meters, her speed is V. Right, okay, so she's down here at some distance, X meters. So we just need to work out all of this. And she's got a maximum of 69 meters before she smashes into the ground. So hopefully everything will reach a conclusion before she gets to 69 meters. All right, by considering energy, show all of this. Right, so the energy that we've got is, we're starting with GPE. Let's put maybe our, yeah, we'll put 0 GPE at the top. And that is going to kinetic energy plus elastic potential energy. This is our transfer that's happening. So we're going to have a half mv squared plus a half kx squared over L is equal to the change in the gravitational potential energy, which is our mgh. So that's sort of our general equation for all of this. We need to start whacking in all of the numbers on all of this. So I'll multiply everything by 2 because I'm not a big fan of having fractions sitting around. So we've got 70v squared plus, what was k? K is 1456. 1456 x squared over our natural length of 26 meters divided by 26, and that, oh, it's not x squared because the extension, I mean it is x squared, but we're using different x's here, so let's be careful here. So the extension is going to be x minus 26 because we've got to go 26 meters before it starts extending. So we take that off of x, which we're measuring from the platform at the top, and that has got to be equal to 2 times m, so 140 times g times x, and that is an actual x again. So yeah, we need to be clear between the x that we've used here, which is the extension, so in inverted commas, and the x, which is the distance that the woman has actually dropped from the platform, which is this x here. So we just need to be clear about the difference between those when we're filling everything in. And that's fine now because we've used that x minus 26 that we got in the bracket here. That's the extension. And then this x on the right hand side is also the same x. So that's all fine. We can use the equation that we're trying to show, this here as a guide. So we're going to want to divide everything by 14 to get a 5v squared. So yeah, and 14s do go into 1456. So let's divide everything by 14. So 5v squared, that's going to be 104, lots of 14 going into that. Oh, and then we divide by 26 and get 4. So 4x minus 26 all squared equals 10gx. Now it's just a case of expanding out this bracket and rearranging everything. So 5v squared, that's going to be equal to, because they've got that on his own on the left hand side here, so let's just start matching up the formats. We're going to have a 4x squared that we need to take off, so that's that bit, so let's put that in the gap, minus 4x squared. We're going to have a 26 squared multiplied by 4. Okay, so that is gonna, I suppose we could work that out in our heads. What we're gonna have, 625 plus 51, so 676 times 4, 2,400, 2,680 plus 24, 2,704. So yeah, we're gonna have to take that off, minus 2,704, and then we've got minus 52 times 4, so minus 208, which we add on, so 208x plus 98x is 306x. That's using 9.8 for G. If we're using 9.81, then we've got an extra little bit that we'd add on, but we're using 9.8 for G in order to get that. So that has shown that. So that's done the first part of the question and used up pretty much the whole page. There's quite a lot for 4 marks. It's yeah, a bit harsh. Why is the expression found in part A not true when x takes values less than 36? Okay, right. Well, that's not true because we don't have, the chord isn't taut, is what it's saying. We need to have the chord beyond 26 meters, otherwise we're just getting a straight interaction between GPE and kinetic energy. So because there's no elastic potential energy until chord is taut. So that bit's fine. Find the maximum value of x. Right, the maximum value of x is going to be when she's reached the bottom and has turned around and started going the other way. So we're going to have an instantaneous v equals 0. So maximum value, so that's maximum value of x is going to be when v equals 0. So we're just solving this 4x squared minus 306x plus 2704 equals 0. I know we can divide everything by 2 there, not by the 4. We can divide it by 2, but let's not try and do anything clever. We just stick that in the formula to get what x is. I don't really fancy trying to factorize something that's got 1,352 in it or whatever it is. So let's just put it into the quadratic formula and get 66.3 meters. So not bad. Find the distance fallen by Carol when her speed is a maximum. Okay, so maximum speed means we've stopped accelerating. We need to have the acceleration is instantaneously 0 because I mean she'll start going back the other way. So the acceleration is going to be changing from positive to negative from the point of view of accelerating downwards. So we need to have that the weight is equal to the tension at that point. And then we're going to have, because of our Newton's second law, we're going to have 0 acceleration. So acceleration equals 0. That's when we're going to have maximum speed. So we need to have our tension, which is 1456 multiplied by the extension, which is x minus 26, over the natural length, which is 26. That's just using Hooke's law. Extension over natural length multiplied by modulus of elasticity, if I can say it right, and that's got to be equal to the weight. So we just need to solve that for x. So multiply through by the 26, divide by the 1456 and add on 26. I'm just saying all of that so I can type it into the calculator and get x equals 38.25. So yeah, so that's all fine. So at least she hasn't hit the ground, which is something. And I could have maybe made it a little bit more daring for her and got her close at that 69 meters, but you know, 38.25, still a long way to fall. Hence, find Carol's maximum speed. So that's just putting x back into this thing here, because x is greater than or equal to 26. We put that in, and then we can get what v is. So yeah, when x equals 38.25, v equals 25.1 meters per second. Let's put a unit on that one as well. So yeah, that's actually quite a lot of work for not very many marks. I suppose 10 marks all in all. But yeah, fairly straightforward stuff really, except maybe, I mean, sometimes you have to be used to this one here is maybe a little tricky of thinking of, well, when are you going to get a maximum speed? Some people, as soon as they see things to do with maximums, they're inclined to go to differentiation. I mean, you could start differentiating this, but it wouldn't be very much fun. So keeping an eye on the fact it's only 2 marks, there's going to have to be some quicker way of doing it. And yeah, an acceleration. You get this with oscillations. I know we haven't got onto oscillations yet. I'm doing it in a later topic. But the more you look at oscillations, the more you get used to that interaction of the maximum velocity is at 0 acceleration and the maximum acceleration is at 0 velocity. You know, you've got that interaction when things are bobbing up and down on a rope. So that's something that we're going to see more of when we get to looking at oscillations in more detail.